Hello students, I'm coming to you with the next video lecture on Chapter 5, which covers testing hypotheses. This is the first video lecture in the series. In today's video lecture, we will discuss the following concepts. The concepts of sample, population, and sampling, the concept of inferential statistics, alternative explanations for the relationships between variables, 3 types of hypotheses, and errors in hypothesis testing. At the end of this video lecture, I will invite you to check for your understanding of these concepts. In terms of learning objectives, by the end of this video, you should be able to understand and explain the difference between a sample and a population. Understand and explain the concept of inferential statistics. Understand and explain alternative explanations for relationships between variables. Understand and explain the 3 main types of hypotheses. And finally, understand and explain errors in hypothesis testing. Let's begin by discussing the difference between a sample and a population, as well as the concept of sampling. A population, uppercase N, is an entire group of people, or what is referred to as the universe. A sample, or lowercase n, is a subset of the population. In statistics, we typically study samples because it is often not feasible to gain access to the entire population of interest. Now let's discuss the concept of inferential statistics. Inferential statistics are used to 1, test hypotheses, and 2, draw conclusions or make statistical inferences about a larger population based on data collected from a sample. In order to make a statistical inference about a population, we need to have a representative sample that resembles the population. If our sample is representative of the population, then we can use the results we glean from the sample to draw conclusions or make inferences about the population. So in the process of hypothesis testing, we must ask ourselves questions such as, does the relationship that exists in the sample also exist in the population? Is this a true relationship, or is this so-called relationship a fluke? If a relationship is present in the sample, it doesn't necessarily mean that it is also present in the population. In order to safely and confidently make inferences from the sample to the population from which it was drawn, we have to ensure that this relationship cannot be attributed to any alternative explanations. So now let's discuss some of the possible alternative explanations for relationships between variables. There are several alternative explanations for the relationship between variables. They include rival hypotheses or confounding variables, measurement bias, measurement error, sampling bias, and sampling error. These alternative explanations can be seen as threats to our ability to make sound inferences and draw accurate conclusions about the relationship between variables. The first alternative explanation is related to rival hypotheses. Rival hypotheses refer to other variables that may have caused 2 variables of interest to appear to be related. This is the same as confounding variables. For example, in the relationship between activity level and weight gain, Weight gain can also be related to age, mental health, diet, genetics, physical health, and a host of other variables. These quote unquote other variables can be considered rival hypotheses. The second alternative explanation is related to measurement. Flaws or biases and errors in measurement tools can produce relationships that are not true ones. It can also mislead us into either overestimating or underestimating the actual strength of the relationship between two variables. The three types of flaws related to measurement are: 1, random error; 2, systematic error; and 3, measurement bias. Let's first discuss measurement error. Before we get into the specific types of measurement error, let's discuss some common sources of error. They include a participant or respondent's mood, a participant or respondent's fatigue, environmental distractions such as noise and temperature of the room, ambiguous or culturally irrelevant terminology, and social desirability, which is known as the tendency to answer questions in a survey in a manner that will be viewed favorably by others. These are some of the more common factors that can contribute to errors in measurement. Random error is bias in measurement that is neither patterned nor consistent. These are chance errors that tend to cancel themselves out as sample size increases. This error is difficult to detect and correct because it is not easy to identify exactly where the error exists. Take this survey as an example. On the left-hand side are the respondents' actual responses to the survey. But perhaps the respondent was fatigued or distracted during the administration of the survey, and their true responses are actually the ones on the right. If the survey were administered under different circumstances, perhaps their responses may be different. This will be considered random error because it is not patterned and therefore difficult to detect. Systematic error is bias in measurement that always occurs in one area. It is consistent and patterned, making it easier to detect and correct. These errors are not by chance and tend to not cancel themselves out as sample size increases. Take this survey for an example. On the left-hand side are the participants' actual responses to the survey. But perhaps the respondent again was fatigued or distracted, or possibly even misunderstood some of the survey questions during the administration of the survey. And their true responses are actually the ones on the right if the survey were administered under different circumstances. This will be considered systematic error because it is patterned and therefore easy to detect. Now let's discuss measurement bias. There are three main types of measurement bias: acquiescence bias, social desirability bias, and cultural bias. Acquiescence bias is produced when respondents to a survey have a tendency to agree or disagree with all survey items. This is sometimes referred to as yay saying or nay saying. Social desirability bias is produced when respondents to a survey provide responses that make them look good or that are politically correct, even if they are not truly representative of their beliefs or attitudes. Cultural bias is produced when a data collection instrument must be translated into another language, and certain terms do not translate very well, leading to misinterpretation. Now let's discuss some ways in which we can go about minimizing biases in measurement. To address cultural bias, we can pilot test our measurement tools with the group we are intending to study in order to seek feedback and clarify relevancy of survey questions. This strategy is thought to aid in minimizing misrepresentation, or rather misinterpretation, of survey items, which can lead to random error. To address acquiescence bias, we can include survey items that are both positively and negatively worded. Take the survey on the left as an example. The first item is positively worded, and it reads, "On the whole, I am satisfied with myself." On the other hand, the second item is negatively worded, and it reads, "At times, I think I am no good at all." This strategy is thought to encourage respondents to read each item carefully, avoiding the tendency to respond yes or no to all items, which can lead to systematic error. To address social desirability bias, we can include in our instructions to respondents statements such as, "There are no right or wrong answers." We can also arrange the items in our survey in a way that flows from the least sensitive questions to the most sensitive questions. Both of these strategies are thought to encourage respondents to provide responses to survey questions that reflect their true attitudes and beliefs. So here are some key takeaways as it relates to measurement tools. In order to make the most sound inferences and draw the most accurate conclusions, we need measurement tools that are: 1, short and succinct, clearly written, free of jargon and unfamiliar terminology. 2, we need measurement tools that are also culturally sensitive and relevant. And 3, designed in a way that minimizes random and systematic error. Finally, we also need measurement tools that are designed in a way that addresses biases related to social desirability and tendencies toward acquiescence. The third alternative explanation is related to sampling. Poor sampling can produce relationships between variables that are not true ones. It can also mislead us into either overestimating or underestimating the actual strength of the relationship between two variables. Two types of flaws related to sampling are sampling error and sampling bias. Before we discuss errors and bias in sampling, we need to first discuss what sampling is. Sampling is a process of selecting cases from a population for in-depth study. It is usually not feasible to obtain data from all cases, as mentioned previously. So we tend to study samples chosen from the population of interest instead. If the selection of cases is done randomly, the data obtained from the sample are assumed to be representative of the entire population from which it was drawn. If the selection of cases is not done randomly, the data obtained from the sample are assumed to be biased and unrepresentative of the population from which it was drawn. Overall, randomization is the key to sample representativeness. There are 3 types of random sampling methods: simple random sampling, stratified random sampling, and systematic random sampling. Now let's discuss sampling bias. Sampling methods that are inherently biased, or sampling bias rather, is the systematic distortion of a sample drawn from a population. Sampling bias typically results from the method of sampling used and not the sample itself. A sample is biased if certain members are underrepresented or overrepresented relative to others in the population. Random sampling methods are used to minimize issues of sampling bias. Sampling methods that are inherently biased and tend to produce unrepresentative samples include snowball sampling, convenience sampling, purposive sampling, and quota sampling. We will discuss sampling methods in greater detail during the spring semester in research methods. Now let's discuss sampling error. Sampling error is the natural tendency of all samples to differ from the population from which it was drawn. Two samples, even if randomly selected, will invariably differ from the larger population. A key rule of thumb is the larger the sample, the smaller the sampling error. And the smaller the sample, the larger the sampling error. In statistics, we are always estimating the larger population. The larger our sample size is, the more accurate our estimation of the population is. The illustration on the left depicts the idea that all samples are drawn from a larger population. Each sample can differ in size as well as measures of central tendency and variability. The illustration on the right depicts the idea that as our sample size increases, our sampling error decreases. All in all, larger samples tend to more accurately reflect the population from which they are drawn. Here are a few key takeaways related to sampling error and sampling bias. In order to make sound inferences and draw the most accurate conclusions, we need samples that are, one, large enough to provide a good estimate of the population. Remember, the larger the sample, the better estimate of the population it provides. And two, we also need samples that are representative enough to provide a good estimate of the population. Also keep in mind that random, unbiased samples provide the best estimate of the population. Now that we have discussed all of the alternative explanations that can influence our conclusions about the relationship between variables, now let's discuss the different types of hypotheses that can be posed about the relationship between variables. There are three main types of hypotheses: null hypotheses, one-tailed hypotheses, and two-tailed hypotheses. The null hypothesis suggests that two or more variables will not be related. For example, a null hypothesis might be, among an elderly sample ages 60 and older, there will be no statistically significant relationship between gender and self-esteem. A one-tailed hypothesis suggests that two or more variables will be related, and it also predicts the direction of the relationship between those variables. For example, a one-tailed hypothesis might be that female elderly ages 60 and older will have significantly higher levels of self-esteem than male elderly. With one-tailed research hypotheses, Researchers tend to use words such as positive, direct, negative, inverse, higher than, lower than, greater than, or less than to predict the relationships between independent and dependent variables. A two-tailed hypothesis suggests that two or more variables will be related, but does not predict the relationship between those variables. For example, a two-tailed research hypothesis might be, among an elderly sample, ages 60 and older, there will be a statistically significant relationship between gender and self-esteem. I would like to follow this explanation with a brief note on formulating hypotheses. Hypotheses are educated guesses that are typically informed by previous research studies or existing theories. This information can provide the basis upon which we formulate our hypotheses. While this is not always the case in research, and there are some studies that do not base their hypotheses on previous research studies or existing theories, typically researchers tend to have some basis upon which they formulate their hypotheses. And again, this includes previous research studies and existing theories, which set the tone for the formulation of hypotheses. Now let's talk a little further about hypothesis testing. In statistics, we never test one or two-tailed hypotheses directly. Instead, we test the null hypothesis, which always predicts that there will be no relationship between variables. We either reject or fail to reject the null hypothesis. Ideally, we want to reject the null hypothesis and claim statistical support for the one or two-tailed research hypothesis. Here's an example of how we go about testing the null hypothesis. Again, let's say that hypothetically, our null hypothesis is that among an elderly sample, ages 60 and older, there will be no statistically significant relationship between gender and self-esteem. And hypothetically, our two-tailed research hypothesis is that among an elderly sample, ages 60 and older, there will be a statistically significant relationship between gender and self-esteem. Now that we've formulated our hypotheses, we will then in turn test this hypothesis using inferential statistics. So let's say that hypothetically, again, our result is that there indeed is no statistically significant relationship between gender and self-esteem. If this were our result, then we would in turn fail to reject the null hypothesis. Statistical support in this case was not found for our research hypothesis. Note that we never refer to a hypothesis as proven. We only state whether we have found support for it or not. This is because all knowledge is subject to refutation and can be disproven at any point in time. Now let's discuss two types of common errors in hypothesis testing, referred to as type 1 and type 2 error. Type 1 error occurs when we reject the null hypothesis and conclude that a relationship between variables in a sample exists, when in fact it really does not. This is known as a false positive. Type 2 error occurs when we fail to reject the null hypothesis and conclude that a relationship between variables in a sample does not exist, when in fact, it really does. This is known as a false negative. This is an illustration that helps to further explain these concepts. As you can see in the picture on the left, the doctor tells a man he is pregnant when he really isn't, which is a type 1 error or false positive. In the picture on the right, the doctor tells the woman she is not pregnant when she really is, which is a type 2 error or false negative. So in summary, we have discussed the following concepts in this video lecture: the difference between a sample and a population, as well as the concept of sampling. We have also discussed the concept of inferential statistics. In addition, we have discussed alternative explanations for the relationship between variables. We have also discussed 3 types of hypotheses, including the null hypothesis, one-tailed research hypotheses, and two-tailed research hypotheses. And finally, we have ended this discussion by covering the concept of errors in hypothesis testing, which include type 1 and type 2 error. This is the point at which I invite you to check for your understanding of these concepts. You can do this in one of 3 ways: by simply completing the form on the left and clicking the submit button, or copying and pasting the link into your browser or scanning the QR code with your cell phone in order to complete this survey. I hope that this has been helpful, and I look forward to seeing you in the next class.